Section: Introduction. We're fascinated by the significant strides made by large language models, LLMs, such as GPT-4. These developments have led to a need for more effective benchmarks to evaluate and compare LLMs, as traditional ones are no longer as useful due to the LLM's expanded capacities in natural language understanding and generation. Benchmarks should not only define and measure various abilities, but also map out the relationships between these abilities to offer insights on how to acquire and improve them. Also, we must ensure that variations in training data, which can be very diverse, do not affect the fairness of evaluations. Another aspect to consider is how we present evaluation results. The metrics we use should be easy for users to understand and make useful observations from. We must also find solutions to issues such as evaluating tasks with large search spaces and conducting human evaluations, which can be laborious and difficult to reproduce. In this context, we've proposed a benchmark called Knowledge-oriented LLM Assessment, or KoLA. We've structured it around three main elements: ability modeling, data, and evaluation criteria. Our focus is on measuring the world knowledge of LLMs, as we believe this plays a crucial role in their performance and is a major challenge for LLMs. Our approach is to go beyond just testing LLMs on a wide range of tasks and topics, and instead delve into the relationships between knowledge-related abilities to provide a reliable evaluation. For this purpose, we've designed a 4-tier cognitive ability taxonomy. Drawing from learning theories such as Bloom's taxonomy, we have organized these abilities into 4 levels: knowledge memorization, knowledge understanding, knowledge applying, and knowledge creating. This structure provides specific feedback on where an LLM may be lacking, and allows us to explore how LLM's learning mechanisms compare to humans. We have chosen 19 tasks that focus mainly on world knowledge about entities, concepts, and events. For the data, we've taken an innovative approach. We use both known and evolving data sources. Some researchers use unpublished or machine-unreadable data, hoping that it hasn't been included in the LLM's training data. But with the rapid pace of LLM development and their voracious appetite for data, this may not be a sustainable strategy. Instead, we propose evaluations on newly emerging data and maintaining a continuously evolving benchmark. In KoLA, we host a new competition season every 3 months, each season using 500 recently published articles as our evolving data source. We also use Wikipedia as a known data source, allowing us to evaluate learning efficiency and generalization abilities of LLMs. Finally, our evaluation criteria are structured around a contrastive evaluation system. Traditional benchmarks often report separate metrics for different tasks, making it hard to compare results. In KoLA, we present standard scores across tasks, relative to other evaluated LLMs. This makes it easier for a wider range of users to understand. For more experienced users, we also provide the absolute metrics. A particular challenge is evaluating knowledge creation, as this involves distinguishing between valid knowledge and false or invented information. To address this, we've developed a self-contrast metric that focuses on whether the generated completions align with the presented knowledge. In KoLA's inaugural season, we evaluated 21 widely used LLMs, including commercial models like GPT-4 and Cohere Command, and open-source models like GLM-130B and Llama. Our findings were insightful, showing for instance that larger models tend to remember more knowledge, and that alignment can improve a model's higher-level abilities but might detrimentally affect memorization. We also found that open-source models generally lagged behind their commercial counterparts. We invite more LLMs to participate in KoLA's evaluations and contribute to its future seasons. All relevant information, including data, leaderboard, and participation details, are available publicly. We hope KoLA will guide the development of increasingly knowledgeable LLMs and assist developers in choosing the most suitable LLMs for their knowledge-based applications. Section Summary. The recent breakthroughs achieved by large language models, LLMs, like GPT-4 have led to the need for better benchmarks to effectively compare and test them. The proposed Knowledge-oriented LLM Assessment benchmark, KoLA, evaluates the world knowledge of LLMs using a 4-level cognitive ability taxonomy and a contrastive evaluation system. The benchmark includes evolving data sources and a self-contrast knowledge-creating metric, and the experimental results show intriguing observations, such as larger base models tend to memorize more knowledge. Alignment unleashes the potential of larger models in higher-level abilities but may harm memorization, and open-source models exhibit overall inferiority compared to commercial models. Section: KoLA Benchmark. We're talking about a benchmark called KoLA, which stands for Knowledge-Based Language Model Abilities. The primary goal here is to measure how well artificial intelligence systems, specifically language models, can handle knowledge-intensive tasks. When we say knowledge in the context of AI, we mean a wide spectrum of information that includes facts, events, and skills. This information is used to determine how intelligent an AI is. Recently, with language models showing promising results, we have seen the emergence of more holistic benchmarks that evaluate these models in a way similar to human subject exams. That's where our KoLA benchmark comes into play. In the sea of evaluation datasets available, we argue that it's crucial to look at the different layers of abilities these models have and how they interconnect. Rather than simply categorizing these evaluations based on the specific field or difficulty level, we should consider them in a broader sense. This concept isn't new. Cognitive scientists have been supporting this idea for several decades now, leading to the development of many cognitive learning theories. Given the ongoing debates about high-order thinking, we've decided to simplify things a bit. We've chosen 4 basic cognitive processes from Bloom's learning theory to structure the tasks in our KoLA benchmark. First, there's knowledge memorization, or KM, which tests how well the model can recall known facts. This is similar to past tasks that probed the model's knowledge. Second, we have knowledge understanding, or KU. This aspect looks at how well the model can comprehend the inherent knowledge within texts, something akin to traditional information extraction tasks. The third aspect, knowledge applying, or KA, is all about assessing how effectively the models can use their knowledge to reason and solve problems. So, this is assessed by giving the models various reasoning tasks. The fourth and final aspect is knowledge creating, or KC. This tests the model's ability to produce new, logical knowledge based on what it already knows. The evaluation isn't just about how well the model generates content, fluency and such, but also about the coherence and correctness of the knowledge it creates. To sum up, our goal with the KoLA benchmark is to offer a more comprehensive evaluation of knowledge-based abilities in AI language models, beyond what typical evaluations provide. We believe this nuanced approach to evaluation will prove more effective in assessing and enhancing AI capabilities. Section Summary. The KoLA benchmark evaluates language models' knowledge-related abilities through 4 cognitive processes: knowledge memorization, knowledge understanding, knowledge applying, and knowledge creating. These processes aim to assess the model's ability to recall known facts, understand underlying knowledge, employ knowledge for reasoning and problem solving, and create novel and reasonable knowledge. The evaluation goes beyond assessing the generation quality of the model's output. Section. Data source and selected tasks. We're concerned with the evaluation of large language models, LLMs, and the potential biases or unfairness due to variations in the data used for training and testing these models. To address this, we're proposing the use of 2 distinct data sources. Firstly, we have our known data source, which is based on Wikipedia. Wikipedia, with its more than 6.6 million English articles, is a trusted and rich source of information widely used in the training of language models. We believe it's fair to assume that every LLM has been trained on Wikipedia, and we've chosen it as our known data source. Since many LLMs state they can only provide answers based on content published before 2021, we're using a high-quality subset of Wikidata, known as Wikidata 5M, that links to the 2019 version of Wikipedia. Secondly, we have an evolving data source. Given the time it takes to train these models, it's unlikely that new data will be incorporated quickly. Therefore, we've designed an evaluation mechanism that constantly pulls in web content published in the last 90 days. This approach helps ensure a fair evaluation of the LLM's performance on unseen content and whether they involve knowledge updating modules like external search. Based on these 2 sources, we've selected and constructed 19 tasks, which we call a season of KoLA. Each season requires a minimum of 500 articles. For the first season reported in this paper, we've chosen 2 types of data: news articles and fictional novels. To ensure high quality and efficient annotations, we randomly pick 1 task at each level to annotate the new evaluation dataset. We aim to ensure most of the test sets are not public to maintain fairness. Now let's discuss the tasks across 4 levels. For knowledge memorization tasks, we evaluate an LLM's ability to remember facts by probing them but using our data sources. Given a set of 3 related data points in Wikidata 5M, we create a sentence using a relation-specific template and let the LLM complete it. We're also interested in whether an LLM's knowledge memorization correlates with training frequency. The second level of tasks, knowledge understanding, evaluates whether LLMs can understand various genres of knowledge from texts, including concepts, entities, entity relations, events, and event relations. We utilize a variety of methods for this, including concept probing tasks, named entity recognition, relation extraction, event detection, and event relation extraction. Knowledge-applying tasks evaluate an LLM's ability to apply multi-hop reasoning, specifically over world knowledge. We use different progressive Wikipedia-based datasets to measure this capability. We have tasks like Hotpot QA, 2Wiki Multi-Hop QA, Mosaic, KQA Pro, and KORC to measure these abilities. Finally, we have knowledge-creating tasks, which evaluate a model's ability to generate knowledge-based text. We believe the crux of creativity in narrative text generation lies in describing subsequent events, so we assess a model's creation ability by their event knowledge hallucination in generated texts. For this, we've built an annotation platform and conduct detailed event annotations on both Wikipedia texts and articles in the evolving data. We'll provide more details regarding annotation processes and task demonstrations in the instructions section. Section Summary. The authors propose a distinctive data source for evaluating LLMs, consisting of a known data source, Wikipedia and Wikidata 5M, and an evolving data source, web content published in the last 90 days. They construct 19 tasks in KoLA, including knowledge memorization, understanding, applying, and creating tasks, to evaluate LLM's performance on various genres of knowledge from texts. The tasks are based on both Wikipedia texts and articles in the evolving data, ensuring a high level of fairness. Section. Contrastive Evaluation System. Our evaluation system incorporates a couple of interesting aspects, including standardized scores based on comparative model analysis and an innovative metric called self-contrast. This system not only evaluates the generation quality but also monitors for any false knowledge generation, effectively enhancing the evaluation of the output. Let's start by discussing the standardized overall scoring. We noticed that different KoLA tasks have varied metrics that are not directly comparable and might confuse less experienced audiences. This issue isn't unique to our setup. It's seen in other language model benchmarks like Big Bench Hard and MMLU. To resolve this, we decided to use standardized scores, making KoLA results more applicable. In essence, for a given task set D, containing tasks D, and an evaluated model set M, containing models M, we choose the most representative metric for each task. This allows us to compute the performance score of model M on task D. The standardized score, referred to as Z, is then calculated. This score is the performance score from which we subtract the mean of all scores and divide by the standard deviation of all scores. To make these scores more comparable and readable across tasks, we perform a scaling operation to adjust all results to a range between 0 and 100. The final scores are given by subtracting the minimum of all Z scores from a Z score, dividing by the difference between the maximum and minimum of all Z scores, and then multiplying by 100. Now, let's discuss the self-contrast metric. Evaluating the creation of knowledge is not just about the quality of generation, but it's also about judging if the generated knowledge is accurate and sensible. To address this, we came up with a unique self-contrast metric. In our setup, C stands for the preceding context, R for the human-written succeeding text, and K for the knowledge in R. Each model is asked to generate two completions. First, a freely generated completion, T, given the context, C, and second, another completion, T_K, given both the context, C, and the foreknowledge, K. If T and T_K are very similar, it suggests that the model can independently generate highly sensible knowledge content. This method doesn't require human evaluation and doesn't emphasize the model's ability to mimic a specific writing style. To avoid issues with the model ignoring the knowledge, K, in the prompt, we define the final knowledge creating score as the average of the similarities between T and T_K, T and R, and T_K and R. The similarity between two texts is calculated using a commonly used measure called Rouge L, F1. Section Summary. The contrastive evaluation system proposed in this paper includes standardized overall scores based on relative model comparisons and a unique self-contrast metric that can automatically evaluate knowledge hallucination and enhance generation evaluation. The standardized scores are calculated using a representative metric for each task and then adjusted to a range of 0 to 100 using min-max scaling. The self-contrast metric evaluates the model's ability to spontaneously generate highly reasonable knowledge content by contrasting two completions generated by the same model. Section. Availability. We've built an online platform that provides a variety of services to our community. These include keeping you updated with the latest competition news, helping you visualize evaluation results, and making it easy for you to create new models or tweak previous submissions. The dynamic nature of our KoLA data source means that with each season, new results and rankings will be generated. We also ensure that selected results from prior seasons remain available to the public for reference. Getting involved with KoLA is easy, and there are two main ways to do so. First, you can be a competitor. In this role, we encourage open participation each season, and all you have to do is provide your model's APIs or parameters. To help with debugging, we give out 5 high-quality examples for each task. Please note, however, that we do not allow local evaluations to prevent potential issues with test set leakage and unfair overfitting of datasets. Second, you could be a contributor. We have a special interest group, the link to which you can find on our platform's About page. This group serves as a platform for volunteers with ideas for analyzing results, refining models, or improving benchmarks to come together, share their suggestions, and help develop the tasks. Additionally, we offer supporting tools to facilitate interactions with KoLA. These include 1. An easy-to-use function that allows competitors to independently manage the in-context prompts for each task while providing a single model API. This makes it easy to submit and modify work. 2. We also share the code and tools we've developed for data visualization and standardization. This will aid in reproducing results and performing other types of analysis. 3. Lastly, we provide a data access API which assists authorized users in accessing the constantly updating data and results from previous seasons. Section Summary. The KoLA platform offers a range of services to the community, including competition news updates, visualizations of evaluation results, and convenient access to suit new models or modify previous submissions. Researchers can participate in KoLA evaluations as competitors or contributors, and supporting tools such as easy-to-suit, result reproduction, and data acquisition are also available. Section Experiment. We experimented with different language models, evaluating their performance in the first season of KoLA. We considered 2 types: open-source models, such as GPT-J, GPT-Neox, Bloom, T0++, Llama, GLM, UL2, Flan T5, Alpaca, and Chat-GLM, and API services like GPT-3, Instruct GPT, Cohere Command, J2 Jumbo Instruct, GPT 3.5 Turbo, and GPT-4. The model sizes ranged from 6 billion parameters to 175 billion parameters, although some of the model sizes have yet to be officially confirmed. Our analysis showed that GPT-4 and GPT 3.5 Turbo held a significant advantage, with standard scores averaging 2.06 and 1.32, respectively. A few interesting patterns emerged from our results. Firstly, for models without alignment or instruction tuning, like GPT-J and Bloom, there was a strong relationship between the model size and its ability to remember knowledge. The larger the model, the better it performed, which supported findings from previous evaluations. Secondly, models that had undergone alignment or instruction tuning showed a significant increase in correlations between their larger sizes and higher-level abilities. However, there was a decline in the correlation between the size of the model and its performance on lower-level knowledge memory tasks. This observation might highlight the so-called alignment tax. Thirdly, we noted a noticeable gap in the performance of open-source models compared to commercial models like GPT-4 and GPT 3.5 Turbo. Open-source models scored an average of -0.29, falling below the overall average. Among these, only FLANT5 maintained a competitive edge across most tasks. This suggests the need for stronger collaboration and support for larger, higher-quality open-source models in the future. From our experiment, we made several new observations. For instance, tasks within each level were highly correlated, suggesting a hierarchical structure to language model abilities. High-level tasks, particularly those involving understanding and reasoning, relied heavily on the knowledge memory level. Also, we found that results from evolving and non-evolving tasks were linearly correlated, implying that our evolving datasets were reliable. We noticed that the performance gap between known and evolving data was more pronounced in lower-level tasks, but less so in higher-level tasks. This could suggest the model's improved generalization capabilities, and its ability to perform divergent reasoning beyond simple data fitting. Lastly, we manually annotated results from the knowledge creation tasks. This involved reading the contexts and prior knowledge, then evaluating the model's outputs in terms of overall quality and faithfulness. Our findings indicated a significant correlation between the self-contrast metric and the faithfulness of the created content. Removing the self-contrast metric led to a significant decrease in the correlation with human-judged overall quality. We believe that this metric could play a crucial role in future investigations into generation abilities. Section Summary. The KoLA evaluation of language models, LLMs, included open source models and API services, with GPT-4 and GPT 3.5 Turbo performing the best. Model size positively impacts memorizing scene knowledge, but alignment unleashes the greater potential of larger models in higher level capabilities. Open source models lag behind commercial closed source models, and KoLA design factors show that LLM abilities possess inherent hierarchical structure and that evolving datasets enhance generalization capability. Manual annotation of knowledge creating tasks shows a notable correlation between the self-contrast metric and the faithfulness of created content.